a look at your handout, right? Alright, let's go. Marquis, we get flexible done on what? Alright, good.
I know.
I'll just
Somebody tell me that.
Alright, let's go. Get flexible done on Alright, so wave motion, right? Wave motion is a means of transfer of energy from one point to another without there being any transfer of matter between the waves. Waves can be classified as being mechanical or electromagnetic. Mechanical waves are produced by disturbance in a material medium and are transmitted by particles of the medium oscillating to and fro about the equilibrium. Right? Mechanical waves are therefore require a medium material for their propagation. For example, water waves, waves in a string, sound waves, and waves in a slinky, right?
What?
Electromagnetic waves. Electromagnetic wave consists of a disturbance in the form of varying magnetic and electric fields. No medium is necessary, however, EM waves travel more easily through a vacuum than through matter. Here we have some examples, right? And you have to remember the spectrum of which order it's in, right? Anybody remember which one the largest is?
Yes.
Largest wavelength is what?
Radio.
Radio, and the smallest is?
Gamma.
Gamma, right? And if you have visible light, to the right of visible light is what? It's the higher wavelength. Ultraviolet. Higher wavelength. Sure. Infrared. Remember, red has a higher wavelength than violet, right? So infrared has a higher wavelength than ultraviolet, right? Okay, next. Some of the characteristics, period. So a non-periodic wave or pulse of a single wavefront is produced by a single disturbance. Periodic waves is produced by a succession of period disturbances which give rise to a wave train, right? So for example, if you see in this, right? If you see in lines, right? All those lines represent what we call a wave train, right? Right? Energy movement, we have progressive waves and we have stationary waves. Anybody remember the two types of progressive waves? Anybody else? Transverse and longitudinal, right? Yeah.
Yeah.
Right? So a progressive wave is one in which there's a transfer of energy from the source to places around it, right? A stationary wave is one in which there's no net transfer of energy, however, there's an interchange of energy. So energy now being transferred from one point to the next. Okay? But there's an interchange. And energy being converted from one point, right? Right? Our focus is going to be on stationary waves. So you're going to recognize that most waves they would move like this, right?
Yeah.
Right? But a stationary wave just oscillates right here. It stays in the same position and it moves up and down. Okay? So for a transverse wave, the oscillations are perpendicular to direction of travel, longitudinal wave in the same direction. What type of wave we have here? Look at the sling. Right? Oscillating in the same direction, right? Right? Oscillating in the same direction. Parallel. Right? It's a longitudinal wave, example of sound wave, right? There's one more. Remember that's the one, huh? But suppose I wanted to use a slinky to get a longitudinal wave. What would it look like? Daria? Suppose I wanted to produce a transverse wave, sorry. What would it look like on the slinky? Underneath here is a longitudinal wave. Using a slinky. Firstly. No, how it will look? How the diagram will look? How the diagram look? Up and down, right? Right? So it will look something like that. What is called the high points again? Crest and the low. Nice. Here we have an example of a displacement position graph, right? And how do we define a wavelength? How do we define a wavelength? Distance between two crests, two troughs, or the length of a whole cycle, right? Length of a whole cycle. Right. Anybody? Can I read off period here? On this graph? It's a displacement position graph, so you can't read off wavelength, right? Right? You can only read off. Right. But if you look here, you have a displacement time graph, and you can read off what? Mr. Ryan, can you go and sit on the back seat? Or sit on the front? All right. So right, this is a displacement time graph, length of time for one cycle period. Okay. What is frequency again, Faith? What is frequency of a wave? Formula wise, F is equal to 1 on 2. Nice. Right, so here we have some parameters to go over. Displacement is the vector distance on a wave from its position. Displacement is the vector distance from the equilibrium position. Amplitude, maximum displacement, period, time for one cycle, right? In a period, there are T waves moving one wavelength, right? Frequency, number of oscillations in 1 second, right? And that's the formula. What's the SI units again? Hertz, right? Nice. Okay. So I want to focus on phase. Right? The phase of a particular point in our oscillation is the measure of the fraction of the oscillation that has been completed with respect to the starting point, right? So I'm gonna show you exactly. Right? We know my pen chart, right? So let's see a wave looking like this. Right. Let's say you started here, right? The original wave started right here. All right, and then blue. You'll see that? I know. If you start here, right? How much of a wave if this particle is here? If the particle is at B, how much of a wave difference is that in terms of length? Half a wave, right? That's half a wavelength, right? Suppose it was here at C. Quarter wave, right? Nice. And suppose it was here at D. Down here at D. Right? 3 lambda and 4. Right? So basically the phase is a measure of the fraction of the oscillation that has been completed. So if half a wave completed is lambda and 2. Right? We could represent phase in terms of pi or in terms of lambda. Okay, so I'm going to show you an example down here. Oh wait, right here. Look at here. Right? So phase is represented in terms of radians. So one whole wavelength is how much? One whole wavelength is 2 pi radians. Half a wavelength, half a wavelength is pi, right? So that's what I'm pulling it off when I'm doing. That's some minus up charging.
So you have it.
Okay, so let's take a look at the phase difference between two particles in a wave is the fraction of the cycle in radians by which one particle leads or lags the other. So I'm going to explain this using this diagram right here. Two particles which are exactly at the same point in the path of a wave and which are moving in the same direction are said to be in phase. So what is here? Are these two waves in phase? Right, both going in this direction. Are they in phase? Yeah. What about here? What about these two waves here? Are they in phase? So that's like this. Are these two waves in phase?
Which way? Which one? The one
Second diagram.
No.
Not in phase, right? Right? So they are out of phase. By how much? By how much? Right. By half a wave or pi. That's okay? So the phase difference is pi or half a wave. Right? Most of the time they'll be up in radians, right? So it's half a wave. So your phase difference when they completely out of phase is pi. Okay? Yeah, in and out of phase. Anybody remember when is needed? In phase and out of phase? Interference, right? Constructive and destructive interference, right? Right. Here's the formula. If you want to write something, you can write this. Formula for wave the phase difference x on pi by 2 pi.
I did nothing.
Right. So here we have two waves, right? You'll see the formula there, Marquis?
Yeah.
Yeah.
Yes. X now 0, 5, 4.
So it's saying that P leading Q by the phase difference, right? What should I measure the phase difference? All it is they measure the length there, that's x divided by lambda and multiply by 2 pi, right? But here's what they say. They're saying that P leads Q and Q lags P. But the graph not labeled. Can you tell me which is P and which is Q here? Take your time, right?
P leads Q.
Yeah. P leads Q.
Q leads P1.
P leads Q and Q lags P. Take your time.
Oh.
Yeah, you are here.
So which one leading? Blue. Very good. Right? Blue is leading. You can look at it this way as well. Blue occurs first in the timeline. Right? Blue occurs first and then green occurs. That makes me to look at it as well, right? So therefore, blue leading green. Right? So blue is P and green is Q. Right? So all we have to do at any point in phase, we can at any point in the same displacement, we can measure the length divided by the wavelength and multiply by 2 pi, and we shall end up with the phase difference, right? I'm going to try and draw a diagram here. Tell me what the phase difference, right? I'm going in red. I'm going in red, right? Any idea how red looking? You're seeing red wave? Alright, that's not. I mean, that's change, it's a black. Right, look at the black wave there. Look at the black wave, Jacob. Look at the black, try to ignore the blue. I apologize, I'm confused. Forget the blue. Look at the green and the black.
Yeah.
What's the phase difference between the green and the black? No. I know, but what's the phase difference? Pi, wrong. Alright, first things. What is X? X is what? What's the distance between the black and the green? I tell you. What's the distance between the green wave and the black wave? Right, yeah, it's X, right? But how much of a wave is that? It's black and the green.
Yeah, but it's like I'm
Alright. Let's try to go back.
not in there.
Alright, look at the black and the red. Look at the black and the red. How much of a wave is that? I'm gonna just fucking line up this thing. And it's best I can do there. Machine good. Okay, start with X. X is how much? A quarter, lambda and 4. Right? X is lambda and 4, right? And then plug it in the formula. You'll get lambda and 4 and lambda multiplied by 2 pi. Lambda will cancel, so you'll get pi and 2.
What was it before?
2 pi and 4. Oh. But okay with that? Right? And which wave leading again, please? Red or black? Which one leading?
Red.
Red and red leading black, right? Nice.
Black is black.
Right? You're looking at phase difference. What would happen if both waves in phase? Huh? And they should overlap, right? Right? Phase times speed of a wave. Phase times speed of a wave. F lambda. Marquis. Oh God, Marquis, shut up now. Prove that, please. Prove that B is equal to F lambda.
Maybe
Prove it, yeah.
from what above, right?
Use whatever you know to prove V is equal to F lambda. That's close enough. Okay. Outside it's like 400 to 1. I check my glasses.
400. Phone books are. That's the one. I
All six. Can you like last year?
Listen, I will pay $300. I think it extra. It's the Nicholas World Cup, right?
Oh yeah, prove that means. Prove that pass that Arian.
I don't know.
Alright, I'll start here. P is equal to what? P equal to what? No, the normal general formula for speed. Let's start some time. Right, see that well here.
Oh.
That's not the answer. Yeah, you gotta prove it. Start from there. Start from there, right? Can we get? Yes, sir. You might need all that here. You might. But we don't need all that. We'll take now. Look back at the definition for lambda and things. Vishish now, before do you think my please? Anybody get to online? Anybody get to online?
Oh, yeah.
You have to prove V is equal to F lambda, right? Two definitions and you go to go. Two definitions, about 3 lines long.
I got it.
Nice. Right, so distance is what?
Distance is on wavelength.
Right, so if a wave travels lambda, then how long does it take to travel lambda? How long does a wave take to travel an entire wavelength? Period, right? And we know that one on
T. I want the T is F.
right,
A little smart.
a little. All right, nice. So that's it, right? That's how you prove that. But you give it up? It's in the notes, I just. In the notes, I just wanted to try. Right, wavefront. The wavefront is a line on a surface. Sorry, a line on a surface in the part that in the part of a wave. Which all the particles are in phase. Rays are lined perpendicular to the wavefront. So what is here? This here is the wavefront. Right? Those 3 waves there is like a wavefront, right? And perpendicular to that is your ray. Right? So if you want to leave out the wavefront, you can just draw a ray, right? But the ray is normally perpendicular to the wavefront. And it shows the direction of the wave, right? Right, intensity. The intensity is the rate of flow of energy.
So it was square.
Looking here. I was here.
Right, so this is something new, so you should write it. Right, intensity is equal to power of energy per unit time per unit area. So the rate of flow of energy per unit area.
So intensity is equal to power, and
Intensity is equal to power over area. So when we look at intensity later on, you'll recognize that the unit is watt per meter squared. Okay. Right, you'll also recognize that intensity is proportional to amplitude squared. So the bigger the amplitude, the bigger the intensity. Okay, so make a note of those two quantities. Intensity is equal to power on area, and intensity is proportional to amplitude squared. So the larger amplitude, the more intense the wave will be. Alright, Darian, suppose I want to increase the intensity of the wave. What do you have to do?
Yeah.
Right.
by how much?
Up. Make a note of that, right? Intensity proportional to amplitude squared. So if you want to drop the intensity, what to do? Lower the amplitude, right? So what's one of the problems with what's one of the problems with being out the sun? Right?
Hey.
Right? One of the problems, right, is people with sensitive eyes. Right, so sometimes we have people with sensitive eyes, right, and they can't take the sunlight coming to their eyes, right? So what they have to ideally try to do is where the shades is reduce the ones. Right. So technically, when you wear shades, you drop the intensity of the light coming to your eye. Right? So really and truly, what they're doing is they are reducing the amplitude of the light. Well, what is called those type of classes? Polarized, right? Polarized. So polarization is a technique by which they reduce the amplitude of the incoming electromagnetic wave. Yes.
So they are fake polarized glasses.
It may get probably reduced less. Okay, so polarized glasses reduces the intensity of the wave. So
But it didn't block the direction.
yeah, so watch here. Here we have an example of polarizer. Can you see here amplitude decreases? So
I mean, really red light.
watch it there.
But you do lines.
Right now you have red and blue. Right, so it oscillating in two directions. But when you put the polarizer, it oscillates in one direction, so it drop the amplitude. Total, yeah. Right? So when you drop the amplitude, what happens? The intensity will drop. Okay? So here we have an example of a polarizer. We have a polarizer vertical and a horizontal. What would happen when you apply a vertical and a horizontal polarizer? No light passing through at the end. So anybody tell me what a polarizer could differentiate?
So we're going on enough percent. That's not true, okay?
Yeah, but hold on, hold on, there is a hand out. I had out. I don't have your another right? So that wave is fully polarized at the end of the second polarizer, and the third polarizer down. Right? And as Marty said, you can only we could use polarization to differentiate between transverse wave and longitudinal wave. Right, and this study here, longitudinal waves such as sound waves cannot be polarized, and therefore polarization is a phenomenon which may be used to distinguish between transverse and longitudinal waves. Right? So here we have a wave oscillating on a rope, right? Used to and fro in all directions. Waves are produced by oscillations in the vertical planes only as they are moved, as they come out of the polarizer. Right? And then if you rotate the polarizer, it's fully polarized. Here we have an example of polarized glasses, right? So if you look at the light that's unpolarized, look how many directions it oscillates in. So when it passes through the lens, you'll recognize that it's not oscillating as much.
So which
So you
one,
have the two drops, yeah?
which one you wanna talk about for like minimum? So like for maximum dimness, but it's like that you can see the best, but you can see the right. So which like it is very hard that
So what I will do is remove one of the lights and try to remove one light. Take over my light. Right? Yes, so there's final ratio between what you want.
and then the other put it in the
Then you put it in the eye. All right, so that's basically how these waves operate, right? You gotta remember the word superposition. Superposition. Darian? What is superposition, Darian? What is superposition? Right, so basically, if you find the vector sum of two waves, that is your superposition, right? So the total displacement at the point where wave cross is equal to the vector sums of the individual displacements due to each wave at that point. So here we have two examples. If I add these two waves again this way, you're seeing that? Wait, what can I interpret to that? And when you add it next to, that is, what type of wave is this here? The two on the right, what type of wave is that? Tell you, what type of phase is that? In phase or outer phase? Outer phase, right? And these two are in. What would happen? So, what's the phase difference here again? What's the phase? Oh, those are two waves. A half wavelength, but phase different in terms of pi, right? 1 pi. Yes, pi. What would happen if the phase difference is pi on 2? Would you have constructive or destructive? You would have a mix, right? Not fully constructive or fully destructive. To be in between, right? Okay? So the waves, you can just add them up. I think I had a diagram here. Right? So watch it here. It's a little tricky, but look at the dotted line and the broken line. If you were to sum the dotted line and broken line, you will get a solid line. That makes sense? Let's just add a few points, right? So if you add it here, Darian, and here, what you'll get? You'll get 0. Nice. If you add here and here, what you will get? A larger value, right? What about if you add here and next point here? Most likely you get this point here, right? So we can.
Okay then.
Are you okay with that? So that black line there is the algebraic sum of the solid and the broken and the dotted, right? It's a little tricky, but you can obviously see it's different. Alright, no, don't worry, we kinda hard to see that. Right, that's the phase difference, good. Let's take a look at stationary waves, right? So I want to do a little simulation so you will see how it produces. Right? Here's the important part, right? Head up stationary, well, you don't head up, don't worry. Let's look at the simulation first. Online, you're getting any the screen looking okay? It blew you, it's okay. Huh? Oh. What I read. How does that start? Hold on, yeah. Alright, everybody watch here. Right, okay, so we go and observe.
So typical for you.
Right, watch here, please. Excuse I'm saying. And we get that done. Follow watch here, please. Right, watch here. What do you expect? So I'm gonna produce a wave here, right? And I pause it, boy. Alright, so watch this here. I'm gonna produce a wave. So I just produce a wave, right? Audio. Hey, before the wave hit the wall, what do you think will happen? Marquis for wash boy. Watch here now. Right? Okay, so watch this here. Watch this here. So when it hit the wall, it reflects, right? But watch this here. Watch. See what happening there? You'll see that? Watch when the red meet the blue. You'll see a large wave being produced. That wave is called a stationary wave. Right? That is called a stationary wave. And you would recognize that the wave simply going up and down. You'll see that? That is a stationary wave being produced. Watch it here. What I want you to notice as well is that on one end is fixed, the next end is fixed. Those fixed ends are what we call nodes. And in between a fixed, in between two nodes is a antinode. Right? You're not going to see anything at the nodes, but look at the antinodes. Right? Look at those large waves being produced. So what you observe in there is a stationary wave. Okay? Everybody okay with that? Right? But this is when both ends are fixed, right? You all see the node and antinode thing, right? Everybody see that? I don't know how to only happen because right here. A little off there, right? Right? But that is a stationary wave. I tell you, see that? Everybody okay with that?
Yes, sir.
Yeah. Yeah. Yeah.
So, by definition, so that's stationary wave, groups,
I'm gonna go check, but what you can tell me from based on what you observe.
is a wave that basically, and it interact with itself.
Superposition, right?
Just giving.
Right. That's the part. So you're gonna write that for exam, right?
So, question,
For 2 marks.
Okay, so a stationary wave is being produced here.
yeah,
When you have two waves that are in phase, superimposing each other. Okay, and the way that we observe it here is when I don't know what color was first, blue or red,
Right.
right? So when red reflects on the wall, right? The red and the blue, they undergo superposition and produce that large wave. Okay, and notice stationary waves is not moving, just staying up and down. Do you recognize that?
no, so at some point in time, it's
Of course, yeah, yes,
destructive and constructive, that's why you get it flat sometimes.
at some point. All right, so let's change the end, let's reset it. So I have a fixed end. Let's start from a free end. Let's see what will happen. Watch it here. So you all recognize when I had two fixed ends, I had two nodes on the end. What would happen if you have a free end? Antinode will be produced, right? So watch this here. You see it here. Online, you're seeing it, right? Katrina? Hopefully not too slow, but you're gonna go straight to the website and watch it as well later on, right?
Yeah, sure. Sorry.
Right. So watch what happening on the end now. On the end, we have an antinode being produced. That's okay. So whenever you have fixed ends, they will produce nodes. Whenever you have open ends, they'll produce a antinode. Okay? So the particle are allowed to do whatever it wanted. Behave, right? This antinode, antinode. You always need something to produce the disturbance here.
So, my favorite, like, when they have
Kind of. But as more observed, like if you blow it up bottle and you hear a loud sound, yeah, that's resonance, so that's a stationary wave being produced. Stationary wave technically is resonance. Okay, it oscillates, but at those points, oscillate much larger. All right, nice. I'm gonna show you the next one here. Watch this here. See this here? Here's the next version of it. Right? And if I start with a antinode, watch what will happen. The wave looks like that. Antinode on the end. We're gonna draw all of them now. Are you okay with that?
I find out we hard to do.
Yeah, well, I'm gonna do this one quick for you now. All right, nice. So let's jump into stationary wave, right? Online, are you okay with that? Brian? How do I remove this one? I just take off stuff. Brian, I follow it. Right? Quick definitions, and we're gonna draw all these stationary waves, right? Stationary waves are produced by the combined effect of two identical waves traveling in opposite direction. That is, it is superposition of two waves with the same speed, frequency, amplitude, traveling in opposite direction. Alright, are you okay with that? definition, right? Superposition results in points where the displacement is always zero. These are called nodes, midway between it, maximum, right? That's the antinodes. I'm gonna draw diagrams that missing for you now, right? So those are stationary waves. Let's see if we could explain a few of them, right? So watch this here. Oh gosh, it's in stick again.
We don't forget.
Alright, so watch here. So Darian, so watch here, right? So a wave, so a stationary wave. This is one of the ways that we could draw it, right? Right? Because the stationary wave moving up and down, right? Sometimes you will see people draw the waves like this. Right? So you draw it broken here. Huh? What's up?
Yeah, man.
Draw it out. Right? So here you have your node, your antinodes, your node. All right. So your wave will look like that, right? The wave oscillated, and your first stationary wave looks like that. All right. So watch this here. We need. Watch here now. Right? We need to understand how to draw these stationary waves between fixed points. One end open, two ends open, right? We have to learn to draw the stationary waves and do calculations on them. So
the frequency, the velocity, or which one?
the wave, we're gonna draw the wave and then calculate those things after. All right, so watch here. Darian, watch here, please. Right. So what you will recognize that if I were to change the frequency on that simulation, right? The wave that you're viewing will change. And here's why. The first resonant or the first stationary wave that you will observe between two fixed points, we call that your first harmonic. Right? We call it your first harmonic. So your first harmonic is the wave that produced with a node here and a node here. Why a node here and a node here? Because both ends are fixed, right? So if you look back here, right? How much of a wave is the first stationary wave that can be produced with a node on one end and a node on the next end? How much of a wave? You're saying that? Half a wave. So at the first frequency or at the first harmonic, the first stationary wave that you will observe, right? It's called your first harmonic and it looks like this. That's okay? That is your first harmonic. That's your first harmonic. So as you start increasing the frequency, the first stationary wave you will see will look like this. That's called the first harmonic. If you keep increasing the frequency, you will see a next one. Right? Anybody can tell me how much of a wave would be there? Try to remember, I didn't specify this, right? But the length of the string or the length of the wire, whatever we're using is the same. So the first time you're going to see half a wave. As I keep changing the frequency, you're going to see a different size of wave, right? So what would it be? What would it be? It must have a node and a node. So your first one will be here, your second one is here. You must have a node on the next end. Pay attention now.
Wait, so what question?
Right? The question is, as we increase the frequency on this string, right? Imagine, right? So you'll see that in a little while. So if I have an oscillator here, right? If I have the oscillator here, right? This length of string not going to change. But the size of the wave or the size of the stationary wave being produced will change as they increase the frequency this oscillating at.
Wow.
Right? So the first one, the first harmonic that you're going to observe is called your first harmonic, or sometimes it's called your the first harmonic or your first. I forget. First harmonic or your first. I'll come back to that. Overturn, first overturn, yes. First overturn, yes. Right. So as you change the frequency, what you're going to observe here is going to change. I am trying to show you how to figure out what the first harmonic will look like, or first overtone, or what the second harmonic will look like, and what the third harmonic will look like, and so on. Huh? Right. So the length of the string is L, right?
Yeah.
And what we observing here is half a wave, right? So half a wave is L. So the wavelength is 2L. Yes. Right? But I didn't reach there yet. You just jumped the gun. Right? Right. So now we continue to change the frequency. We continue to change the frequency. We have to get a node and a node here. So the next observable will look like this. Right? So the next observable will look like that. A whole wave. And as Yash said, we technically adding on a half a wave all the time. Okay? So this whole thing here is the same string, same L, but now I have a whole wave. So now lambda is equal to L. Okay? If I were to do it here now, node and node, how will it look? Right? It will now be 3 lambda on 2 is L. So lambda is equal to 2L on 3. Right. Why did we do this? Because the reason we did this is that this will be oscillating at a particular speed. So if we know the speed and we know the wavelength, we can definitely find the frequency. And frequency is what, Javid? Frequency is equal to F1 lambda. Sorry, V on lambda. So it's V over 2L. Right? So the first harmonic is observed when the frequency is V over 2L. That's okay? Can we predict when the second harmonic is heard? It'll be V over L. Okay? Just to make the formula look nicer, it'll be 2 on 2, right? Right? And third harmonic is, it will be 3V over 2L. So the fourth harmonic is what? 4V on 2L. That's all. That's okay? So based on which harmonic you want to observe, you can adjust the frequency. So for those who into music and things, if you want to hear a particular harmonic, all you have to do is adjust the frequency. Like if you're blowing into a flute probably, and you adjust the frequency, you'll be able to hear different harmonic. Now you are no gosh boy. Right? So again, this is when both ends are fixed. Yeah?
Because I put my own software.
No, fourth one will be 2 waves. You just keep adding and adding and adding and adding.
No, but would it be the same formula?
Same formula. No, it will change, right? It will be 4V on 2L. When it reach 4, it will look like this, right? Right? It will keep looking like that. You just keep adding on a half a wave, half a wave, half a wave. So technically, you could have an infinite number of harmonics. Huh? Yeah, things will start to decrease after a while, and it will be low and it won't really. All right, but again, these are when both ends are fixed. So since Darian know what's going on in class, that's Darian. Come on the board and draw the harmonics for one end open. Come. Why is it come and stand up here? Come fast. Come on, George. I'll help you draw the first one. All right. So if one end open, right? Next end close, right? So if one end open is, what will be observed at that point? Another antinode. And if the next end close, right? So look at the diagram and tell me how big of a wave is the first harmonic, where you must start with the antinode and finish at a node. Look at this first diagram here. Look at the first antinode possible and the first node. And tell me how big of a wave is that. Look at this here. First antinode, look at your first node. And tell me what size of a wave is that? Half a wave, 3/4. So here was half a wave, right? Half a wave? Are you sure? How much is that?
Yes.
How much is that? To be exact. How much is that? Quarter of a wave, right? Quarter. So it will look like this. One end open, one end closed. So it will start here. Antinode, node. How much is this again? How much is this again? How much of a wave is this? Quarter of a wave, right? So lambda and 4 is L. So L is sorry. So lambda is equal to 4L. So the frequency here, will be V over 4L. So I want to see who could tie this in. Look at this frequency, look at this frequency. Who happening first? Who happening first? This happening first? For the person who can explain that why, based on what we did last week, but again, anything in the copy. Anything. Right. We did something last week, right? Right? We did something last week. And I would like to know how this explains it. Think about what's happening here. And the hint I gave you was this frequency was this happened before, right? We did this last week. Huh? I want to know why. Why it is this happening at a earlier frequency?
Alright. So
And you have to draw the reference to what we did last week.
okay, so
Take your time to do the chance. That's it. Huh?
I
Online, you can attempt as well. Yeah.
what price they get online?
Online, get anything you got.
What do you think?
Valid for 1 month.
What?
No, online. You can come anytime in the next month and get it. Huh? Yeah.
Alright, so what's the question you ask?
So the frequency this occurred at is before this. at an earlier frequency than that, right?
Yeah.
Why?
So, well, it have to do with with the energy and in the coupon meeting, right? So.
Go ahead.
And energy maximum, like it has a constant maximum. So when it is coupon, that we can have constant maximum.
Now you're mixing up simple harmonic. I'll give you the next thing. Right? We talked about resonance last week. Right? And these are the resonance waves.
Yeah.
Right. Think about what we talked about, yeah? Try it. You got nothing to lose? You got nothing to lose. Something on resonance we did last week. Huh?
I think.
So, maybe.
Based on resonance.
That's what we done.
What?
Was it a question why the
Anybody online have anything?
so was it question exactly? Why that happened earlier than the other one?
I don't know. I don't know. I just wait out the stuff. Keep it now.
I don't know hybrid.
Like now, but like it was still came out. It was still
Well, close.
I was some videos
I'm missing something I asked about it. Well, close. If I give you one point, you'll guess it.
So here was nothing. The street art in the context of resonance and damping is influenced by the interplay of the deep and resonance. Number one, resonance. I'm even worried.
The maximum amplitude. So, right, so that would be the 2,000 that everything that you are oscillating would be so I still ask you.
I said thing you say, but it's still missing what I'm talking about. You're real close there. Yeah? Nah. Alright, time out now. So I want you all to draw two diagrams, but you're real close, right? So I'll look at the walk downstairs and pick anything. Downstairs. Not the cafe, anything downstairs or the Alright, so what's here? Alright, so that's close. So they have a half, right? Yash have a half and Dylan have a half and something. A half and nothing else yet. Next thing we get summarize. You'll get a whole like pick something. Alright, anyway, here's what. So you're close there. Here, by opening it up, we introduce damping. Right? And by introducing damping, yes, drops the amplitude and it also decreases the frequency at which the resonance occurs at. So if you remember the graph, when it undergoes the damping, the natural frequency and driving frequency will happen a little bit before. Okay? So that's why the frequency happen a little bit before. Right? And the amplitude a little bit smaller, of course. Very good. Right. As I said, as you move down here, you just increasing it by half a wave, right? So I want you to draw second harmonic, third harmonic in the book. Okay? Before you do second and third, somebody can help out here?
Yes,
Two ends open. What will it look like? What you will have here?
One of the Hickory.
What you will have on this side? Antinode or node? And what you'll have on this side?
Antinode.
Look at the diagram. How to draw it?
Yeah, maybe
I'm saying?
One.
Right. So antinode coming down here to our next antinode.
that look like a one, bro.
Right? Watch here. Antinode to antinode. Antinode to antinode. That's okay?
Then it's called African natural.
That, yeah.
When it's called them pass anyway, but African natural.
Antinode and antinode. No, no pecan shock again. Not in stationary waves. Okay? Right?
Is that possible?
How much are we with what is that? Yeah. Both ends open.
Oh.
What do you mean?
Like,
It harder to observe, but because it will be a much smaller frequency. Right? But you can have not much smaller now, you might be able to observe it close to this. You just have a container open to see. It's possible in a straw. Yeah, if you blow into a straw at the right frequency, you might be able to hear the resonance.
So
Yeah, I think it's that you have just here
Like
coming up.
yeah, this here, it's here.
Yeah, you do.
We
You
don't
hear
get
it.
it properly, but yeah.
Let me see where you can hear it again, boy.
So,
The conch is technically like that, but it have a whole lot in accent. Actually, music man now, where is that? Huh? But you kind of control who man. So the record more like this. What?
Like I think because actually I don't know it.
No, I say you produce a sound. You producing a sound. Right, George, draw all of them, please. Draw here and here, here and here. Draw the second harmonic, third harmonic, second harmonic, third harmonic. Right, so you're looking when they talk about stationary waves, what they're talking about.
Yeah.
First and second and third. Right, most important thing, at a fixed point, you have a node. At an open, you have an antinode. And as you go from first to second to third harmonic, you always increase by lambda 2. Okay? Write that down, please. Okay, after you draw it, write a little summary. This is observable. I'm trying to remember this practical one.
But the,
Two ends open.
yeah,
Two ends open. Right, we're going to move into calculation next day, right? And the calculation based on these principles. As you go from one harmonic to the next, everything increases by half a wave. Right, so in your book, I want you to draw all three harmonics for all the three situations.
oh, go ahead and put one of them. So the twins, and twins, when you want to talk, people you be seated in a pipe. Hey.
Right, so hopefully you have all. So remember, you must have a, so if you're not seeing it, my advice is to just show this and just take out what you need, right? So you have an antinode and node. Now they want to get an antinode and a next node on the end. So you add on a half again. Sorry. Sorry. Right, so add on a half to this, right? So if you add on a half to this, it will be here. You'll see that? If you add on a half again, it will be here. Okay? So if I add on a half, I would be antinode, node, something like that. That looking kind of bad. Okay, so you have your antinode here and you have your node here, right? Right, again, this is 3/4 of a wave, right? So L is equal to 3/4, right? 3 lambda and 4. Do the same thing here, do the same thing here. Okay, most important, most important, they all increase by lambda and 2. Okay, any harmonic, they increase by lambda and 2. Okay, did you draw? By it.
Yeah, that's what I'm trying to say there.
Right, next day, what we'll do is we'll go into the part tables, right? Right, because that's the most important thing, right? That you can draw them properly and then. Okay, so that's your first harmonic, second and third. If you look at the handout, if you actually read that, you would see. Right, but if you look at the handout,
It's all in the talking. The same like the sport.
right, so watch here. Right, these are the diagrams here for the different harmonics, one and open. Right, and you got all the formulas here for you. You don't have to learn it. You don't have to learn these formulas, right? So all you have to learn to do is from this find lambda and then find for frequency. Really easy. And here is when you have 2 times open. Got it here up? Yeah. So next day we will take a look at past papers. Do you have enough time now? So next day we look at the calculations, right? So we look at the calculations and we'll run through the Form 5 stuff, interference, refraction, diffraction, and things. Before we jump into the heavier stuff. Next week we have class like normal, right?
Good, next Friday.
Yeah. Next week Friday we have normal, we have Friday.